Thank you so much for deciding to stay in this room. I hope that you chose because of the content of the talk and not because of the comfy seats in here. And you have decided to kind of dive the depths and brave distributed consensus with me today instead of braving the cold winds out there in Montreal. So my name is Heidi Howard. I'm a researcher at the University of Cambridge, and for the last 4 years, I've been studying distributed consensus. I'm absolutely fascinated by the problem of distributed consensus. It's one of the most kind of fundamental and powerful primitives in distributed systems. It's really widely used, but it's really subtle, poorly understood, and in my mind, often poorly implemented. And today, what we're going to do is we're going to take a step back. We're going to revise a theory that's been around for 3 decades, and we're going to prove that some of the most famous algorithms, namely Paxos, are actually conservative in the way they approach distributed consensus. So we're all here today because we subscribe to this distributed dream. We believe that these systems, if done correctly, can be performant, scalable, low latency, reliable, dependable, consistent. But we're not naive. We know that we can't have absolutely everything we want. We can just take a little look at the academic literature. Here's 2 papers by one of my favorite authors in the field, Nancy Lynch. On the left, there's 100 impossibility results in distributed computing. There's a whole paper, 100 things you can't do. And on the right-hand side, we have this famous paper, the FLP result. This is the impossibility of distributed consensus. The ironic thing here is that this paper saying that consensus was impossible is what motivated researchers to spend 3 decades designing consensus algorithms. So if you want a bunch of academics to spend their time solving your problems, you should write a paper saying it's impossible. So this gives my students nightmares. This is what it looks like in reality. This is the different layers of consistency that are available, and that we've tried to kind of, the effort here has been to systemize them. And this is complicated. This is difficult stuff. It would be great if we could just have that linearizability thing at the top, and we could just assume we have strong consistency and move on with things. And that's what we're going to be looking at in this talk. This whole talk, we're just going to be looking at how to decide a single value. There are some servers that store the value, and clients that are going to read and write the value. That's it. The thing that makes this seemingly simple problem so interesting is the weak model that we're going to be using. So we're not going to be assuming that our hosts are reliable. If we send a message, might get there, might not get there, might be duplicated, might be reordered, might be dropped. Our hosts may answer us, they might not. Their clocks may drift. We make no assumptions about synchrony. In fact, the only assumption that we're going to make is that the system is non-Byzantine. What that means is that the nodes will follow the algorithm as implemented. This is not a talk about blockchain. Sorry. So in the current reality of consensus, I broadly kind of divide it into 2 groups. There is the classic Paxos model. So this is, invented by Lamport in the Part-Time Parliament paper, and it says you can achieve consensus in 2 phases using a majority of participants. And it's an algorithm that's talked about, it's an algorithm that's taught and researched, but it's rarely implemented as is in distributed systems. In practice, what we use is multi-Paxos, and we see these ideas also in view-stamp replication, in ZAB, which is the algorithm behind Zookeeper, or in Raft, which is the algorithm behind systems like etcd. And this selects one of the clients and says, you the boss. You're in charge, you're going to make decisions. You're the single point of serialization in this system. The big advantage of selecting one of the participants as the leader is that we can now achieve consensus in 1 round trip. However, all of the decisions have to go via this leader. In contrast, classic Paxos could achieve consensus in 2 round trips, but consensus does not need to go via a kind of leader. So I absolutely love these set of quotes. So this first set of quotes is by Leslie Lamport, and I kind of would summarize this as being the theory community's perspective on Paxos. The Paxos algorithm, when presented in plain English, is very simple. The Paxos algorithm is among the simplest and most obvious of algorithms. In fact, this consensus algorithm follows almost unavoidably from the properties we want to satisfy. You couldn't help but derive Paxos when you're looking at distributed consensus algorithms. It's like tripping up over it. It's just there, and there's nothing, you couldn't even avoid it if you tried. Now let's take a look at what the systems community has to say about it. There are significant gaps between Paxos and the needs of a real-world system. And this is engineers at Google who are saying this, by the way, smart people. Despite the existing literature on Paxos, building a production system is a non-trivial task. That's their way of saying it was hard. And obviously, there's the Paxos paper, the Raft paper. Paxos is exceptionally difficult to understand. The full explanation is notoriously opaque. Few people succeed in understanding it, only with great effort. We found few people who were comfortable with Paxos, even among seasoned researchers. We conclude that Paxos is neither useful for building systems or for teaching. Great. So I would say that the limitations of these two kind of families of consensus algorithms that we have are twofold. Firstly, there's the subtlety of the algorithms. This is what makes them difficult to understand and difficult to implement correctly. And then there's the performance issues. So fundamentally, Paxos relies on majorities. Majorities are great when your system has 3 servers, when your system has 5 servers. What about if your system has 100 servers? What about if those servers are distributed across the world? Classic Paxos is able to achieve consensus in 2 round trips, but it might take more. In fact, we can't prove that these algorithms will terminate, hence the FLP result. A multi-Paxos is a very centralized algorithm. That leader limits the throughput of the system. In fact, every time we add another server or another pair of servers to the system, the throughput of the system goes dramatically down. This is the opposite of a scalable system. And that leader is also a single point of disruption. It's not a single point of failure because we can cope with it failing. But when it does fail, we are going to have to do quite a bit of work to find a new leader, to restore state, and to get the system up and going again. So in today's talk, I'm going to be telling you about the research that I've been conducting over the last 4 years, which is about revising the theory of distributed consensus. In the first part, I'm going to show you an abstract solution to consensus based on a mutable state. This immutable state allows us to then go on to prove that Paxos is conservative in 3 key ways. And in the third part, I'm going to be showing you 3 new algorithms for consensus. And these algorithms are able to achieve that coveted result of consensus in 1 round trip, whilst tolerating minority failures from any client. So if we had 1 server, this problem would be completely trivial. A client sends a message with what they would like the value to be to the server. The server writes that value into a register and responds to the client. Another client comes along, they wish for it to be B, but it's already been set, so it's A. Deal with it. What we'd like to do is have multiple copies, so we can have multiple servers with multiple registers, but we can easily end up in a scenario where we have a split vote. So in this case, we have 3 servers. It's represented in this kind of table to save me doing too much drawing. We've got 3 servers, and 3 clients have come along, each with a different value, A, B, and C, and they've written it into the register. Now we have a split vote, and we haven't been able to reach a decision. What we could do is then have clients retry and start editing values, but this quickly becomes very complicated. And this is where we may break away from the existing literature. Instead of having a mutable register here, we use a set of immutable registers. We represent this as a table. Each column is one of the servers, and then the registers are kind of the rows. We refer to each row as an epoch for reasons that will become apparent soon. Each register can contain either a value, a nil value, which I'm using for just like this hyphen here, or it hasn't yet been written to. And what this means is we've basically kind of got a built-in history of what's happened in the system, and we have more information, which allows us to make more informed choices. So clients can come along and they can write these registers on the server. But when has a client done enough work to say that the value has been decided? When is there enough copies? When have we achieved fault tolerance? Like many engineers before me, what I'm going to do is decide to not have an opinion on this. To remain general, I'm going to say that a decision has been reached when a subset of servers, which we're going to refer to as a quorum, have the same value at the same epoch. I'm using the word quorum here for now just to mean a subset, not requiring intersection. We'll look at whether you do or do not need to require intersection later on in this talk. So here's an example. We see the server table up here, and at the bottom we've got this thing called a configuration table. So this shows the mapping between epochs and quorums. So here we just say, for all epochs, we're using majority quorums, so what people will be familiar with. And if we look at this table, we can see that a decision has been reached at epoch 0, and a decision was reached again at epoch 2. And both of those decided the same value. Great. Here's another example. This time we have different quorums for different epochs. So epoch 0 requires everybody to be involved, all 4 of these servers. Epochs 1 onwards just require 1 pair of servers. And here we can see a decision has been reached at epoch 1, and a decision has been reached again at epoch 2. However, we haven't really achieved anything at this point. We can still have multiple values be decided. So on the left, at epoch 1, we have 2 different values decided at the same epoch. And on the right, we've got 3 different values decided, all on different epochs. So what we're going to need to do is we're going to need to put a rule in here that restricts when clients can write values to ensure that all these decisions are always for the same value. And firstly, we're going to deal with this scenario on the left-hand side. So before a client writes a value, they need to ensure that there is no other decisions that are different from the decision it's working towards, either in the same epoch or in any previous epochs. So we're basically using induction here to ensure that there are never 2 decisions that are different. So dealing first with when we have different decisions at the same epoch, that was the scenario on the left. There are 2 ways that we can deal with this. Firstly, we could allocate epochs to clients and say each client has kind of a disjoint subset of epochs that they can use. That way only 1 value will ever be proposed. And this is the approach that's used by Paxos. Secondly, we could use non-exclusive values. So this is where we say, write what you like, but those quorums at a given epoch intersect. That way we know only 1 decision is going to be reached. This is what's used by, I think, algorithms like fast Paxos. So we can take a look at some examples of this. So for exclusive values here, we've added a column to our configuration table that says which clients have been allocated which epochs. And we can see that a decision has been made both in epoch 1 and in epoch 3. In contrast, we can have non-exclusive values. Here we're using majority quorums. At epoch 0, we do have 2 different values that have been written, B and A, but because we were requiring a majority of people to have the same value, we know that only one of them would have been able to succeed. And in this case, it was A. And we can even use a hybrid of both approaches, and this is where this technique becomes really powerful. So at epoch 0, we could say, anybody can use epoch 0, but you have to use all the servers for your quorum. That trivially satisfies the quorums intersect property. And then we can say for epochs 1 onwards, we've allocated them this time to 3 clients in a round-robin fashion. And we use quorums that are 2 pairs of servers. So we've dealt with this scenario on the left. So we now can ensure that there isn't going to be multiple decisions at the same epoch. But there can still be different decisions different decisions across different epochs, and that's what we're going to deal with next. So far, we've been talking about the state that exists on the server. What we can do is we can have each client store a copy of this server state table that we've been seeing. Every time a client reads from a server and learns a piece of information, such as this register contains A, that piece of information will always be true because those registers are immutable. That is really the power of this technique, is that once you learn something or once something becomes true, it remains true forever. So clients can come along and they can read any register that's on a server, and these clients can also write nil into registers that are on servers. The reason why you might want to write a nil is that if you've got a quorum and you want to ensure it's not going to reach a decision, you want to write nil into one of the registers and you can basically block that quorum. So the clients have their own state table, and when they learn that when they learn that a decision has been reached, then they can basically return that value. So before a client writes a value, either it needs to be in one of two states. Either it knows for certain that absolutely no decisions have been reached in any previous epoch, in which case it's free to write whatever value it likes. Otherwise, it needs to ensure that all the previous decisions are for the same value as it is now trying to decide. And this rules out the scenario on the right because at epoch 1, the client would not have been able to propose B because A had already been decided in epoch 0. And now we've been able to satisfy those safety requirements using these two rules: the epoch allocation rule that deals with conflicting decisions in the same given epoch, and the client write rule that deals with conflicting decisions across epochs. So I'm going to take a quick step back and see what we've actually done there. So what we've got is this kind of abstract algorithm that we haven't really specified yet, but we've got these rules, and we know any algorithm that satisfies these rules will safely solve distributed consensus. At its core, we've used immutable registers instead of mutable state and monotonically increasing numbers, because I think it's easier for us to reason about, and it gives us a lot more flexibility, and it represents all the information that the system has. So next I'm going to look at classic Paxos and how we can generalize it. So we can implement classic Paxos using this kind of abstraction that we've just described. All the epochs are exclusive, so we're going to allocate them to clients, and we're going to choose to use majority quorums. So a configuration might look like the one shown at the bottom of the slide. For those of you who are already familiar with Paxos, you'll recognize this slide. The Paxos algorithm has two phases. The first phase is kind of like a reading phase, and the second phase is kind of like a writing phase. So in the first phase, it chooses an epoch that it's going to use, and it sends that epoch to all of the servers. What the servers do is they write nil to any previous registers of epoch 0 up to E-1, and returns the highest value and epoch that it has filled. We'll go through some examples in a second. And then in the second phase, once a client has received responses from the majority of servers, it chooses the value with the highest epoch, and then it sends a message, propose epoch E and value V to all the servers. This algorithm then basically repeats, and the servers write the value V at the epoch E. And when the client receives the message accept from the majority of servers, that value has then been decided. So an example of what this might look like in practice. So we've got one client, this is client 1, and we've got 3 servers, and we've got this kind of server table here, which nothing's happened. The system has just woken up and kind of entered the world. The client is going to send a message, prepare 1, so 1 is the epoch that the client's decided to use. And the servers are going to respond saying promise, and the message doesn't need to include anything else. And what they've done is they've written nil into epoch 0, basically blocking epoch 0 and making sure that nothing changes in any previous epochs. The client is then free to choose any value it wants. In this case, it's choosing the value A. It's sending the message, I'm going to propose that you write A at epoch 1 to the servers, and the servers will then write that value and reply with the accept message. So another client then comes along. This client's going to try and use Epoch 2. They send the message to the servers. The servers respond with the greatest epoch that has a value and the value that it actually had. So in this case, at epoch 1, there is the value A. In this case, the client isn't free to choose its own value. It has to choose the value A. So it sends propose A to the servers who write the value and reply with accept. So this generalized version of Paxos satisfies the safety criteria that we specified earlier. We use the epoch allocation rule to ensure that at most one decision is reached in any given epoch. And we use the client write rule, which is where we choose the value associated with the highest epoch at the start of the second phase. So Paxos uses majorities because it requires intersecting quorums. That is to say, any two quorums must have at least one server that is in both of them. But what we can see here is that a client, in fact, can use any quorums it wants, any subsets it wants. The intersection property is that a client in its first phase may need to speak with at least one server from each quorum from epoch 0 to E-1. For those of you who are familiar with some of my earlier work on flexible Paxos, this is basically a generalization of that takes it even further than that. So that originally said that quorums from the first phase don't need to intersect with each other, and quorums from the second phase don't need to intersect with each other. And this is a really powerful result, right? So if the client that had started initially had been client 0, when that client starts up, it can just skip the first phase of the algorithm, because that first phase would have had no impact. There is no intersection requirement to meet because you intersect with previous epochs. If you're using epoch 0, there's no previous epoch. So you can just jump straight into phase 2 and decide a value, and you've just been able to reach consensus in one round trip. Paxos also requires that we hear back from this quorum in the first phase of the algorithm before we proceed to the second phase. But in practice, we can actually often, clients other than the first client can proceed sooner than that without violating safety. So, there we go. When we were looking at this example, the client received these two responses from server 0 and server 2 with promise 2.1a. So that's promise in epoch 2 that I've seen the value a at epoch 1. Actually, this client only needed the first of these, and then it could have safely proceeded. Because once it's received one of these, it knows that at epoch 1, only A could have been decided. And likewise, at epoch 0, only A could have been decided because the other clients will have also followed the protocol. So at this point, after receiving just one message, it could have finished that first phase of the protocol and proceeded. And then there's value selection. So Paxos says that if you receive any values in the first phase of your protocol, in the first phase of Paxos, you must propose that value. But what we can see is that we only need to propose a value if we think that value could have been decided. If we have seen a value, but we can say for certain that it hasn't been decided, then we don't have to bother proposing it. We can propose our own value. And here's an example of this in practice. So here we have 4 servers, and our quorums are 2 pairs. This client has sent out a propose 1 to the servers, and the servers have responded. And imagine they responded kind of in this order, so server 0, server 1, server 3. At this point, Paxos would say, you have to propose B, because you saw B, so you must propose it. But if we take a look at the state table and think about what the client has learned here, we can see that actually B can never have been decided, because the only other member of its quorum told us that they didn't have B. And therefore, we're free to choose any value that we want. This is the reason that we can do these kind of things, is that because we have these immutable registers, all the state that's in the system is basically upfront, laid on the table. Here it is for you as a client. It basically allows the clients to make more informed choices. So in the second part of the talk, I've been able to show that 3 of the requirements of Paxos are conservative. We can actually do this in a bunch of other requirements for Paxos, as well as various other algorithms, including fast Paxos and my own work on flexible Paxos. So now I'm going to look at some examples. So previously we said that you can either have 2 round trips, any client, 1 round trip, leader only. And these are the 2 compromises you have to choose from. It would be great if we could have any client achieve consensus in just 1 round trip. Theoretical results have shown that it's not possible to do this in the general case, so for absolutely like every scenario. But what I'm going to do is I'm going to propose you 3 new algorithms that achieve this result and offer different compromises. And that's really what I want you to take away from this talk today, is that when it comes to consensus, there's a whole breadth of consensus algorithms that offer all different compromises, and Paxos may not be the best compromise for your particular deployment scenario. So a bunch of systems are basically co-located. So each node has both a server and a client. So if you think about something like Raft consensus, each replica in Raft is both a client and a server. You're basically reaching agreement between the members of a set. What we can do is if we configure our generalized Paxos algorithm as follows. So what we've done is we've allocated our epochs round robin, and we've divided our epochs and their quorums so that the first 20 epochs just use all servers, and after that we just use majorities. And what this does is this gives clients basically 2 options when they're trying to reach consensus. They can either take the fast path. This will allow them to reach consensus in just 1 round trip. And they do this by basically executing that first phase of Paxos locally with the server that's on the same node as themselves, and then executing the second phase with all the participants of the system. If this is unsuccessful, for example, if a participant has failed, then the client can fall back to the slow path. So the advantages of such an approach is that, as I said, you can get a 1 round trip, and if 2 clients collide, one of them will succeed and one of them will fail. This does, however, require co-location, although it seems like a lot of systems currently use co-location anyway, so I don't think this is a huge restriction. And 2 round trips are needed if one of the servers is slow or unresponsive. So what if we don't have co-location? What if we still want to achieve 1 round trip with handling minority failures from any client, and we're not co-locating our servers? We can do that. So what we can do is use what's known as supermajorities. So for epoch 0, we could use any 4 of 5 servers. And for epochs 1 onwards, we can use our standard textbook Paxos majorities. Again, we have 2 routes when we're trying to reach consensus. We have the fast path, that's using this epoch 0. You can skip phase 1 entirely, jump straight to phase 2, and propose the value that you want. If you're not successful, however, you have to fall back to using the slow path. This works as long as 4 out of 5, in this case, or any supermajority of algorithms are up, and no collisions occur. Another really good advantage of this algorithm is that if 2 different clients are trying to propose at the same time the same value, they won't actually collide. They'll in fact help each other. And that's one of the really interesting problems with Paxos that people don't talk about very much, is that you can still get collisions even when everyone agrees. The algorithm can literally indefinitely argue with itself when everyone is actually just trying to propose the same value. Sounds a bit like politics. And the downside is that 2 round trips are going to be needed if 2 or more of your servers are down. Bearing in mind that 2 round trips is what classic Paxos was offering us in the first place. So what about binary consensus? So one of the typical examples for consensus is reaching consensus over a binary value, like a lock. Either it's been granted or it hasn't, for example, or a transaction, either it's committed or it's aborted. So what I want to do here is whether we can take the common binary value, so in this case I'm going to just call it 0, and say if we're trying to decide 0, can we get 1 round trip using just majority quorums from any client? So that's like all of the things. And here what we're going to do is we're going to change the configuration up a little bit. And instead of allocating epochs to clients, we're going to allocate them to values. So epochs that are even numbers are allocated to value 0. Epochs that are odd numbers are allocated to the value 1. Then, if you're going to propose a value 0, you can take the fast path and you can skip that first phase of the algorithm and just execute the second phase and get 0 agreed. If it's unsuccessful, or if you were going to propose the value 1, you have to take the slow path. So this allows clients who are proposing the value 0 to complete in one round trip to a majority, to just a majority, no supermajorities, no everybody has to participate. And clients that are proposing the same value, again, don't collide with each other. In fact, they just help each other. This only works, however, in this example with binary values. But what we can do is we can generalize this to any set of values. It doesn't even have to be a finite set or a known set of values, and say there is basically one special value. If this is being decided, we can do one round trip. And if other things are being decided, it's 2 round trips. But in some systems, in some particular scenarios, like you may have one value that's much more common, for example, committing a transaction. And this is what I mean generally about kind of choosing trade-offs that are right for your system and not going for this one-size-fits-all solution that is Paxos. So in this section, we've seen 3 algorithms that are able to achieve consensus in one round trip and tolerate minority failures from any client. These 3 algorithms do have different trade-offs that you're making, but the point that I kind of want you to go away with is that you have choices, you have options, you may have to make compromises, but you can choose what those compromises are. So Paxos is just a single point on a broad and diverse spectrum of consensus algorithms. And when we use immutable state as the basis for designing these algorithms, we're able to generate a large number of algorithms that we can modify and reason about quite easily, and I believe are much easier for developers to implement correctly. This is a lot to take in. When people talks about Raft, they describe one algorithm. I just gave you like 5 algorithms, 3 specific ones and 2 abstract ones that generalize over Paxos. So I know it's a lot of material. I'm happy to take questions now as long as we have time. And I will be around for the rest of the week. And I'm always on Twitter. Brilliant. Thank you.
Any questions?
Stunned faces.
I'm not sure I totally followed everything you were saying, but
I'm not sure I do either. It's fine.
Okay. But where you were talking about you could only propose the same value as in an earlier epoch.
Yep.
Then doesn't that mean that's the value, that's the decision? What else could happen there?
So I think what you're asking is in the second phase of the algorithm, when Paxos, the rule is if you've seen a value, you must propose it. And I was claiming that there are scenarios where we don't have to propose that. The reason is that we don't always have certainty about what's happened in the system before we arrived in the system. Those servers might have failed, so we can't talk to those servers and say, did you make a decision for certain? We've seen kind of a subset of what's gone on, and from that we're inferring whether a decision was made or whether it was not made. Paxos is basically conservative and says, always propose a value that you've seen. What I'm saying here is that we can keep track of the quorums, and then if we find out that we've seen a value, but actually it wasn't decided because another one of those registers has a different value or has nil, then we can propose our own value.
Okay. Thank you.
Any other questions?
In the last part about the binary consensus, you said it would be maybe possible to generalize over the binary value, or did I misunderstand that?
No, you definitely can. So basically all you need is one known value that you would like to be able to achieve in one round trip, and you associate that with epoch 0. And then you can do whatever you like for epoch 1 onwards. So you could just use basic Paxos where you're allocating values to clients as you were, and then you don't even need to know anything about those values. So you just need to know one known value that you want to be kind of special, that you want to be your kind of common use case.